previously a PhD student here in Sheffield, and then I've been an MRC Skill Development Fellow, and then that's kind of on pause. That work is on pause at the moment, but that's what I'm going to talk about today. And then since for the last almost a year now, I've been working on a COVID rapid response grant, pretending to be an epidemiologist, essentially, helping the mathematical epidemiology group here in Manchester deal with all their COVID related work. So I should first mention all the people I've worked with to do this work. So in Manchester, I've been working with Oliver Jensen, who's head of the maths department there, Alex Horsley, who's a respiratory clinician and cystic fibrosis specialist there. And also some of the work was partly done by a summer student we had, who has now gone on to other things. Here in Sheffield, I've worked with Jim Wild and Guillaume in particular on what I'm going to present today, but also I've had worked with the whole of the Polaris group to some extent over the last few years. And that's where kind of all the data comes from that you're going to see. So some background, first of all, on the lung and why modeling it is interesting and useful. So the architecture of the human lung is quite complicated. So airways form this, as you can see, intricate branching tree structure. As you can see here, the white cast here this is a cast of the human lungs. On average, this composes of about 15 to 16 generations of branching airways. So you end up with 60,000 approximately conducting airways, which all feed air to the alveolar region, which is this kind of diffusion dominated region of the lung, where branching continues, and you end up with on the order of millions of tiny little airways at that scale, which are constantly expanding and contracting to bring in air and expel it. And all of this is embedded in this 3D space of your chest cavity, so it has to form this kind of interesting sort of fractal structure to basically efficiently transport as much gas as possible to as big a surface area as possible to facilitate diffusion of oxygen across the interface between the airways and the capillaries. So in lung disease, there's lots of things that can go wrong, but one particular sort of side effect of lung disease, particularly when it's sort of in early stages, that is a potential warning sign that things are going wrong, is that you get localized patches of poor ventilation in the lung. So this is where gas isn't reaching particular areas, and this can often be a sign that some treatment needs to change or some new treatment needs to be introduced, and is generally missed by a lot of clinical tools used to check lung function, such as spirometry, which are quite blunt and don't really pick up these small scale changes. So this is where different measurements come in, like MRI. So this image here is an image of it's hyperpolarized helium MRI images of the lung taken, I think, in a cystic fibrosis patient, and you can see these dark patches of sort of poor ventilation dotted throughout the lung. This is exactly some of the work that's done at the Polaris Institute, Polaris group here in Sheffield. And this can be caused by a bunch of things. In cystic fibrosis, it's often caused by mucus plugging, so airways getting blocked by an excess of mucus, but it can also be sort of airway collapse or tissue fibrosis, airway inflammation. All of these processes can stop air reaching all the parts of the lung. And these people might be able to breathe perfectly normally, especially when this ventilation heterogeneity is not that severe. So there's different kinds of models of the lung depending on sort of the questions you want to ask. So there's a long history of compartmental modeling of the lung, and I'll talk about one of these today, where essentially you treat individual bits of the lung by single ODEs, and that way you can have a model that works very efficiently and quickly to describe transport of gases to different parts of the lung. But it doesn't really capture this complex physiology I've described before. Then sort of starting in the sort of 80s, there's a lot of what was known as trumpet-based models, where you treat the branching airways of the lung as a symmetric tree, and then you can essentially model them all as essentially identical. All the airways in the same generation is identical, and then they form this kind of trumpet shape, you can imagine, where they're getting wider and wider and sort of essentially shorter and shorter. So you're delivering gas over this growing surface area as you branch down the tree. And that's useful to study where the sort of advection diffusion boundary is in the lung, where your advection slows down and your diffusion takes over. And more recently, there's a great deal of some emerging technologies in looking at image-based models and using high-resolution imaging of the airways, and then algorithms to fill out the airways that you can't get from imaging, to build these kind of 3D models of the airway structure, and then using these as a sort of sort of scenario hypothesis testing ground for sort of comparing to imaging data, other imaging data, or whatever it is you're interested in, really. So some examples of uses of these recently is you can image lots of the airways, and then you can almost directly relate the structured airways to the ventilation you would see on MRI. So this is some work that other groups have done, but it's also the sort of thing that we're interested in too. So it's really useful for looking at how lung structure relates to lung function. Okay, so the first part of this talk is some work that we recently submitted and actually just got the review reports back. It's not on the archives yet, but hopefully once we've looked through the reviewer comments, it will be. This is about connecting some, it's about some database modeling to connect lung function data to this sort of MRI imaging data that I've shown previously. Okay, so this has all got a bit overlaid, but that's not too bad. We're going to focus on data from cystic fibrosis patients. So I've mentioned cystic fibrosis a little bit already, but a prominent feature of early cystic fibrosis is that there's an excess of mucus in particular in the small airways, and this results in some poor ventilation to some regions of the lung because it occludes some of the airways, and these become underventilated. One way of measuring this that is more increasingly being used in the clinic, but mostly it's still just a research tool, is multiple breath washout. And this is quite a sensitive technique, much more sensitive than spirometry, which I mentioned before, which is, and what happens here is you have someone breathing into a sort of mouthpiece, and a machine measures the flow rate. This is this black line here, and the subject just uses normal tidal breathing. So this is what you can see on this line here. There's a few big breaths of wash in here, but the idea is you just breathe normally and wash in some tracer gas. So this is just air mixed with a little bit of SF6, and the thing we're measuring here is this SF6, which is just an inert tracer gas. And then the source is then switched just to regular room air, and we measure the concentration of this tracer gas as it's kind of washed out. So as it's turned over and diluted and then washed out of the mouth. And you might think, and it's not obvious how that relates to ventilation heterogeneity, but the point is here, this is one index that's acquired from this is lung clearance index, which is LCI. So essentially it's a measure of how efficiently that gas is washed out of the lung. So you can imagine if you have successfully managed to wash in the gas, and this is partly what these deep breaths are at, you've managed to get the gas to all the parts of your lung, then if there's some parts that aren't very well ventilated, they're going to take longer to empty, and that's going to result in a long sort of tail in your washout curve here. And this is essentially what is measured by this LCI measure. So it's how much gas you have to exhale to get below a certain threshold concentration, which is 2.5% of the original concentration, and that's divided by your lung volume, or FRC volume, so that your resting lung volume. Oh, I don't know what's happened here. I apologize for that. At least the figures come out okay. Yeah, I've got. Is everyone else seeing that strange effect, or is that just mine?
No, it is visible, but I think you can see that it's follow it if you just read through them.
Okay. Yeah, no problem. Okay, so I've mentioned already a little bit this hyperpolarized gas MRI imaging. So this data set is acquired by a subject similar to the multiple breath washout. They inhale some tracer gas. In this case, it's a hyperpolarized helium gas, and then during a short breath hold, they're imaged in an MRI, under an MRI scan, and this hyperpolarized gas shows up very clearly in the MRI scan, and so you can see exactly where in the lungs the gas has reached. And essentially the brighter regions, so regions that are well ventilated, and the less bright regions show those parts of the lung that are not very well ventilated. An example of some of the measures we're going to use to kind of quantify those scans in this study are one we've called ICV, which is the coefficient of variation of the image intensity, so the pixel brightness, and I 1/3, which is the fraction of the pixel brightness that's below a certain threshold. So this one's kind of the width of these distributions. If I plot all the pixel brightnesses I see in the lung tissue, then I'll get a really broad distribution if they've got a sort of lots of ventilation heterogeneity, and a more narrow distribution like the blue one here if it's a relatively homogeneous distribution of ventilation or a healthy lung. For the same two patients here, you can see these. Actually, I think these are real data. I didn't make these up. This is the sort of if this is a probability distribution function, this is a cumulative distribution function. It's essentially the amount of lung that's under that a third cutoff. So that's essentially the size of the proportion of lung that's underventilated, under a third of the mean, I should say. Oh dear, looks like all of my slides are going to be like this. That's not good. Is it, you are still having, are you seeing double?
Worry about it, Carl, we can sort of see it.
Okay. It's a bit psychedelic, but yeah, okay. Okay, well, the model I've been using essentially to study this data, the multiple breath washout data I mentioned before, is a simple compartmental model, as I discussed before. So it's essentially a 50 compartment model. So it breaks the lung up into 50 different regions, which all have some rate of ventilation, essentially, and then you simulate pure advection in these airways, which don't form the complex branching tree structure you see before. You just have 50 separate airways that all join into one, essentially at one point, and the ventilatory region is just assumed instantaneous diffusion. So these are like elastic bags propelling gas up through the airways on exhalation, or into the alveoli on inhalation. And this uses essentially a kind of volume element method to simulate this system pretty quickly, which is what's represented by these little blue discs here of volume going in and then getting pushed through the system. So this uses the nice vector function in C++ and therefore simulates things really quickly. Okay. Well, this is an impossible slide to read, I suspect, with what's happened, so I'll describe it very briefly. So to connect this model to the data we have, the multiple breath washout data we have, we use something known as approximate Bayesian computation, sequential Monte Carlo method. So that is a Bayesian method of fitting, and essentially what you do is you draw parameters from your prior distributions, which we generally take to be uniform. So I'll describe briefly what the parameters are in a second, because I think that comes on. I think that was mentioned on the last slide, but I didn't read it out. So I think it also comes in the next slide as well. But you draw your parameters from the prior distribution, and then you basically test. You run a simulation with your whatever your inputs are, and then test the outputs of that against the data that you have. So in this case, we're comparing simulation predictions, so that gas that's being exhaled at the mouth, we're comparing that concentration prediction to what's seen in the washout data to essentially get the best fit. The good thing about Bayesian methods is that they don't demand that you get a single fit, so you can have your posterior distribution of your parameters can include multiple fits. There doesn't have to be a single mode, for example. You can look at the interdependency between different parameters, and you can look at the uncertainty in your predicted parameters. So not only can you say what you think the best fit parameters are for your model, you can say how good you think that estimate is as well. So we add measurement noise to our model as well to simulate the measurement noise of the device based on the sort of published information about the device accuracy used for the multiple breath washout. Okay, so we're back to hopefully normal looking slides now, which is nice. So, and this is a good slide to have that on, because this kind of hopefully encapsulates everything I've just said in one diagram. So we have the model in this box here, and what we do is we take multiple breath washout data, which looks like this, and we run a model. We start with uniform model parameter priors, which are the lung at the moment. It's a very simple model. It has 3 parameters. It has a lung volume, a ventilation heterogeneity parameter, which is essentially the standard deviation of the distribution of ventilation, and we've assumed that they are drawn from a log normal distribution, and the dead space volume, or the airway volume, so how much of that lung volume is taken up by these airway regions. So it's we draw 3 parameters from those prior distributions. You essentially run this model thousands of times through a sequential process of improving and iterating upon your predictions, and you get to some posterior distributions which best fit this multiple breath washout data. And then from that, what we have is essentially a model of the ventilation distribution. So then we can compare that. So we can then say, right, that's our distribution of ventilation. So this is the black line here. Now we're going to measure it using MRI, and we're going to compare the two and see if if we can validate this method, if this method is a valid way of inferring what the ventilation distribution is from this data, and then comparing it to the imaging data, which is about as direct a measurement, we think, as you can get of the actual ventilation distribution in the lung. So some results of our data set. So we use a data set of 25 cystic fibrosis patients who had both multiple breath washout and MRI on the same day. The multiple breath washout was done in the unusual supine position, so that it was in the same body position as the MRI, which helps to remove some of the differences that can be caused by the fact that people's ventilation distribution changes when they sit up versus when they lie down. And you can pretty much see that in almost all cases we get really quite good agreement. It's worth saying that the mean is kind of meaningless. This is a normalized sort of pixel brightness, so everything's scaled to have mean of 1. But nonetheless, the shapes of these distributions are pretty good overall. There's a few outliers which don't fit very well. The numbers next to them are just a measurement of the goodness of fit of the distributions. So you can see this one's quite large, this one's quite bad, and this one is not so good. But for the rest of them, actually, it's kind of remarkably quite good that the fit that we get is from essentially a completely different data set seems to match up with the imaging. We're back to strange text, but this kind of shows that for these 2 indices that I mentioned before, so the coefficient of variation of the pixel intensity, measured is on the x-axis, predicted is on the y-axis, we get really good mean agreement. So on average, our simulations agree really well. Error bars show sort of uncertainty, and you can see that basically when we predict that ventilation heterogeneity is low, we're very accurate and we're quite certain about that. And then when ventilation heterogeneity is high, we are both less accurate but also less certain about it. So it's quite promising that in one sense, it's promising that we know that our predictions get a bit less accurate as we get increased ventilation heterogeneity, but also it shows that there's room for improvement there. In particular, if we can maybe use more of the multiple breath washout data, or essentially develop more detailed models than this simple 3-parameter case. So this is just direct comparison of those two measures, and these are just some bland Altman plots to show the same information, but this is the difference between the predicted and the measured, and then this is the mean between the two. So the red line just shows that the mean difference is essentially 0 in both cases, but there is quite a bit of variation around that. So we have fairly good predictive power, fairly good agreement, but there's plenty of room for improvement. And the other benefit of this, so one hurdle for rolling out multiple breath washout to the clinic is that data acquisition time can be quite long, especially if people have quite severe or moderate to severe ventilation heterogeneity. Then the tests take quite a while because they have to wash out all this gas, and the test has to be repeated 3 times. And by using this model, we could cut off the data set we found quite early. So what this is showing is on the left here, this is if we were to measure our LCI, which is our traditional measurement of ventilation heterogeneity. If we were to cut that off at different cutoff points, so instead of our 2.5% cutoff, we do it at 5%, 10%, 20%, or 40%. We see that our sort of correlation to the original LCI drops and drops and drops. Whereas if we cut off our data set at the same point, but then run our model on it instead and get our measurement of ventilation heterogeneity, which in this case is our sigma parameter, we see that the correlation is retained really well, basically, even as we cut the data off to a relatively small sample. So it suggests we could very safely make a much shorter data collection time and still get just as robust indices of ventilation heterogeneity and just as sensitive. So it's essentially a sort of simplest case model, but we've shown that it's sufficient for meaningful parameter estimation, and we've verified that against the MRI data. There's some evidence that we've seen that the model limitations impact on the predictions. So there's definitely lots of room for improvement, and hopefully this kind of technology can bring us one step closer to using MBW more widely in the clinic, because if you can run a fairly fast model alongside the data and extract information from a much smaller data set than you would need to traditionally collect, then that means you would be able to make it much more efficient for clinicians to do this thing, and you'd save time and money. The future refinement, I think we want to look at, because we've used this Bayesian approach, we want to look now at model selection algorithms. So using more sophisticated models and seeing if in different scenarios or in different patients, whether different models work better than others in a systematic way, and we can do that using the Bayesian approach. Okay, so I might pause for a second there because I'm going to switch topics quite severely now. So I wonder if there's any questions on that part before I do that.
Okay, I think we can open up to questions. So let's say 5 minutes of questions, and then we'll move on to the next part. Is that okay? Then Carl. Okay. So while others are typing out questions, and I will keep an eye out on that, and I will make whoever is asking the questions a presenter. Can I ask one question to start off with? So you said that you probably already hinted that the MBW, the breath washout based indices, they perhaps can vary for one subject from one session to another, perhaps, and that's why you probably do 3 repeats of the measurement. Is there any attempt at refining the protocol of the experiments such that the patients are doing the same way, and how robust could that be?
Yeah, definitely. And actually, that's kind of one of the motivations of doing this kind of modeling work. So one So it is quite constrained what the patients are supposed to do. They're supposed to breathe a certain amount each breath, and there's a little display on the screen to tell you how deeply you've taken a breath. And if your mask slips and there's any leaks, then the test is void and things like that. But yeah, there's certain things you just can't probably avoid. Like even just posture changes sometimes can change things a bit, especially in more severe disease. Yeah, so there definitely have been attempts to change the protocol and improve the protocol, and that has worked. Like there was this, they didn't used to do this deep breath washing right at the start to get more gas to all the regions of the lungs. That's come in now, and that both speeds up the test and means that you get signals from all areas of the lung, slightly better signal from all areas of the lung, rather than never really getting any of the gas to the problem regions that you want to know about. So that's one thing. But as I said, if you can sort of correct for some of these things with the modeling, so what I don't think I mentioned properly there actually was that what the modeling does here is it takes the flow rate as input. So the flow rate at the mouth is the kind of drive, the input function essentially of the model, and then from that we predict the gas concentration at the mouth. So then if you do have an irregular flow rate or something goes wrong, you can adjust for that. Essentially, your model kind of accounts for that, and it doesn't mess up all your indices, whereas sometimes it can have that effect, which tends to get averaged out over 3 tests, but it can mean that on a test by test basis, it's a bit more robust, I think. Oh, that's the idea anyway. Yeah.
And you also have you also put in a source of like noise to your in the model input, isn't it? And to probably take into account, was it to take into account such kind of uncertainties, or are there any other kind of uncertainties that are there in the testing?
So the noise was just the only noise we included there was a measurement noise. So that was a sort of white noise around the flow curve that's measured, which is about at the accuracy that device can measure the flow at. But there's other sources of noise, sure, in terms of, just inside the patient or whatever, or inside, there's all kinds of things like that can affect the measurement that aren't included in there, and that probably explains some of what that kind of thing is why we're missing, some effects, I guess. That, and we just haven't used a good enough model to look at all the aspects of what causes differences, basically. Yeah.
Sure. Awesome.
Okay.
Thank you, Carl. I've been keeping an eye out on the chat box, but I haven't seen any questions. So maybe we can move to the next part. And really sorry about the ongoing problem with the text. It's definitely my fault. I probably should maybe make it a PDF and then having uploaded. Sorry, I didn't give you enough advance notice that Blackboard does things with PowerPoints.
It's very
your pictures come out very nice.
It's only doing it on half of them as well, but I guess we'll never understand really why that is. I can assure you that I didn't make my slides like that. I don't think maybe it's because I had some animations built into some of the slides, and that's messed things up possibly.
The pictures are coming out very nice though.
Yes, that's the main thing. No one reads the text anyway, right? So it's fine. Okay, so part 2 is some completely different work now, which is very much on the other side of this question, which is how we can make more detailed lung models more computationally efficient, and also just some interesting maths, really. So it's a little less practical, this, but hopefully should be quite interesting, especially for the more mathematically inclined in the audience. So this is looking at now at lung airway networks. And in particular, we're going to use some tools from spectral graph theory to investigate the sort of mathematics of ventilation on these networks. So very simply, we can model the airway tree as a network where the nodes represent branching points and the edges represent airways. The airway tree is almost always dyadic, but it doesn't have to be, but it definitely, in almost all cases, it is a tree. So there are no circuits in the lung. I think it can happen in very rare cases, but generally speaking, it's a perfect tree. So you can, because it's a tree structure, you can think of it as a hierarchical hierarchically ordered. So every airway branches into has a parent airway, and it branches into children airways, and then at the end of the tree, which in this case is kind of the alveoli or acinar regions of the lung, wherever you decide to cut that off, you have some terminal nodes, and those terminal nodes can be defined exactly by can be grouped by their sort of branches that they have in common further up the tree. And we arbitrarily choose branches to be oriented, in this case, down the tree. So from the mouth end up here down to the sort of acinar region or alveolar region down here. So for those of you not familiar with graph theory, I'll just very briefly introduce a few matrices that are important. So there's the adjacency matrix, which describes and degree matrix. So the adjacency matrix describes which nodes are connected to which other nodes in the tree, and the matrix basically say it has a 1 there if 2 nodes are connected, and a 0 there if 2 nodes aren't connected. The degree matrix is just a diagonal matrix, and it tells you how connected each node is, so how many connections each node has. So these are the matrices for this very small tree here. You see node 2 has 3 connections, so it has a 3 in the degree matrix, and it has 3 1s for node 1, 3, and 4 in the adjacency matrix. The incidence matrix is slightly different. So each row now represents a node again, so there's 4 rows, and each column represents an edge. In this case, there's 3 edges, and each column has a 1 for the node in and a -1 for the node out. So this is where this directionality comes in. The node in is node 1 and the node out is V2. An important operator, especially when we're thinking about a lot of physical processes, is the Laplacian, the network Laplacian. So this is the degree. This can be written as the degree minus the adjacency, or it can be written as the incidence matrix multiplied by its transpose. And it kind of looks like the finite element Laplacian you would expect to get from a grid that looks like this, basically. So for example, for node 2, you get a -1 on for all the nodes connected to it, and a +3 for the node in the middle. So it's a very, very brief primer. Okay, this slide's even worse than the previous ones, but that's a very brief primer on graph theory. So how does that relate to the airways? Well, in a very, very simple model of the airways, we could think of the flow as being proportional to a pressure drop divided by a resistance. And in general, airflow is not a Poiseuille flow, which is what we've used here. It's far from it. It's in many airways it's turbulent, or at least transitional. But generally, you can think of it, at least if it's sort of steady and relatively slow. So if we're thinking of sort of normal tidal breathing, then you can think still of each airway as having some resistance, as long as the flow rate isn't changing a great deal, even if that resistance is non-linearly dependent on flow rate in reality. So for this simple case where we're thinking about graph theory operators, we treat the resistance as a linear. Well, this resistance relation is linear, and we use Poiseuille flow for convenience, but you could use a different assumption, a better assumption for the resistance of airways. And in vector form, this can be written as Q, which is the flow rate, is equal to so for the whole network, this is an individual airway. The flow is equal to a pressure drop divided by resistance. Over the whole network, this gives you flow is equal to the inverse of this diagonal resistance matrix multiplied by the incidence matrix transpose multiplied by the vector of node pressures. So you get this is an edge property, this is a node property, and this incidence matrix takes edge things from node things, basically, is one way to think about it. So then if we want to, hopefully you're all happy with equations because the text is pretty hard to read. So if you want to then work out what the flow is over the whole network, then you can multiply that equation again by the incidence matrix, and what you find is you get the Laplacian multiplied by the pressure is equal to the flow on the node, this capital Q, where the Laplacian, in this case, so I said the Laplacian before was incidence multiplied by transpose entity. This is the conductance Laplacian, so it's those two matrices, but it's got this inverse. It's scaled by the inverse resistance of the airways. And if you then apply some boundary conditions to those terminal nodes, in this case, Dirichlet boundary conditions, then what you see is you have some, so it can be split into three parts. So your pressure on your entrance node, your pressure on your internal nodes, and your pressure on your terminal nodes. The flow in and out of the system, well, there's a flux in at the mouth, there's a flux out that goes into the alveoli, and then in the middle, flux has to be conserved on these nodes. At the, at the branching point of your airways, you don't accumulate or lose air. There's a conservation of flow. And if you split your tree up into those three regions, then you can write your different operators like this, where this gamma term here is essentially the resistance of those terminal edges. Okay, and rearranging this to solve for essentially, well, we need to, first of all, we need to remove there's an arbitrary pressure, as there always is with the system, which is Laplacian. There's always one variable, sort of too many, so we have to fix some external pressure. So we just fix pressure in the mouth and define everything relative to that. So we just define the pressure relative to P1, which is the pressure at the mouth. And then you can solve your system for the internal pressure drops, so the internal pressure relative to the pressure of the mouth, and the terminal flux coming out at the going into the alveolar region, and that's all these two equations. Of course, you could instead set your boundary condition on the pressure, and then you would just So you could set your boundary conditions on the flow, and then it's a really trivial system to solve. Because if you set your boundary conditions on the flow, then you know the flow out of every single node out of your system. Then you can just add up basically through the whole tree what flow is on every other branch, and you don't have to do a solve. But if you want to set the pressure at the end, which in some sense is more physiological, because assuming the pressure being applied to this system is roughly the same everywhere, then you need to solve for the flow that's going out of those terminal nodes. Okay, I realize I'm getting a bit close to the end. So there's another way of representing a system that isn't the Laplacian, and this is what we kind of stumbled on in our research, which is of course the Maury operator, because it's introduced in a book by a guy called Bertrand Maury. And essentially, because this system is a tree, you can describe everything in terms of the terminal nodes. So these are the 4 terminal nodes of our tree, and you can describe the whole system as if it was actually just a graph, a complete graph connecting these nodes. The resistance between the nodes is their common resistance on the tree. So I said before that everything can be treated hierarchically. So if nodes are only related by the entrance branch, then the resistance between them is R1. But if they're they're next to each other on the tree, then they have 2 branches in common. So the resistance between them is R1 plus R3. And if we compare that to the Laplace formulation, we can see that this Maury matrix R is equal to this combination of linear operators, where L is this internal Laplacian. And this object exists for any network, but it only kind of becomes useful when your system is a tree, basically. So we define the eigenvalues and eigenvectors of these 2 operators, the lambdas and the mu's for R. So lambdas are eigenvalues of this internal Laplacian, so the Laplacian on just the non-boundary condition nodes, and R, which is our Maury matrix, which is just acting on our terminal nodes. And if we then think about what our boundary conditions should be, then in a very simple model of the lungs, we might suppose that our alveoli essentially act like elastic bags. So we stick a elastic boundary condition basically on the system. So this means that the alveolar region expands with some elastic coefficient kappa proportional to the pressure being applied to it, and we assume that all the bags or all the whole lung is experiencing the same pressure applied to it for this simple model. So then what you find from doing that is that you can write your system as a single equation where it's your Maury matrix multiplied by your flow rate into the so this is the derivative of the volume, so the flow rate into those alveolar regions plus the elastic term minus pressure being applied, and this E is just a unit operator on all the terminal nodes. So it becomes a nice single equation, but it's worth noting that this R matrix is actually a full matrix. So it's not a practical way of solving your system. If you wanted to just numerically simulate this, you would use the Laplacian because it's a sparse matrix and it's easy to solve. But if you're interested in messing around with equations like we were here, then you can write it neatly like this. And what we find, and this is a bit of a messy slide, I admit, but it's actually come out clean enough, is we can then define using this our ventilation heterogeneity in our simple model with in terms of our mode structure of these operators. So in the case of the Maury system, we can write down our delta V here is our max volume minus our min volume. So that's the ventilation of a given terminal node, so a given alveoli, if you will, and then ventilation heterogeneity can just be measured, say, as the coefficient of variation of this thing over the whole lung. And you can see then that we can exactly relate the eigenvalues of that operator to this property. And what we can see if we look at that is actually that any modes where the eigenvalue divided by kappa tau, where tau is the time scale of a breath, is less than 1, have negligible impact on this prediction. So basically only the modes with high resistance are important in this expansion, and we can dispose of the rest. This is where one thing was supposed to appear and then disappear, so that's why, but at least the text is not visible anyway. So this is an example simple network, an example network which is asymmetric, but it's kind of based on physiology, but it's not taken from images or anything. It's known as the Horsfield model of branching, and we take that and we apply some constrictions to it to essentially simulate a sort of lungs of varying levels of ventilation heterogeneity. And what we do is we show that if we cut off, we can recreate the simulations with a very small proportion of the modes. So this is showing agreement between the estimated and the simulated case. So we cut off the modes at 0.1 multiplied by this kappa t cutoff that I mentioned, and we can recreate all these simulations which are different amounts of, which require different amounts of modes. So this shows for the different generations where we apply the constrictions, how many modes we actually need. But bearing in mind that in total there's 30,000 modes roughly in this system, we never need more than 1% essentially to really effectively recreate the simulation. So this suggests that this method, at least for the simple simulation, is really useful for dimensionality reduction. We can represent the whole system with, in many cases, a handful of modes, and essentially do the same simulation, but in a fraction of the time. Oh dear. Okay. Maybe I did have one video. Maybe that's what happened, but that's okay. It's not what you'll see there is some of those airway image-based airway models. Before, you would see one of those growing and filling the space. So we use some image-based models of the airways as well, based on some of the data collected again by from CT by the Polaris group here, by Jim's group. And we run some simulations on those, and we see essentially the same thing. We can vary the elasticity of the lung mechanics, and we can make predictions. So the dotted lines and the lines are our predictions from our sort of reduced model using a small selection of the eigenmodes. I think in this case the top 1%, and the dots are the simulations. So you can see that we get good predictions of all our simulations. And okay, I'm just going to skip that slide. But essentially, we can show you that what you see here is that the simulations agree with the predictions, basically, again. So at the moment, this is all limited to linear models, as I mentioned before, which is not very realistic for the lungs, especially for the large airways. And it doesn't include the compliance of the airways, but that is an interesting next step to try and introduce. We've only considered uniform compliance of the lung here, so you can't have. So at the moment, everything I showed there doesn't have any like patchy elasticity, which is another feature of lung disease. You get some stiffer regions of tissue and some less stiff regions of tissue, but that can be generalized with this method. Actually, that's not too difficult to show. This Maori operator I've said is limited to tree networks, so that limits its usefulness to other biological systems at the moment. But we are thinking about ways of generalizing that, and that's something actually for the next summer project I'm going to run this summer. Get a student to start thinking about that, and then we'll maybe take it away and run with it if it works. But the good thing about this is it's used to understand these large-scale models that take a reasonable amount of computational power and time. Instead, we can kind of characterize the airway network in one go with this spectral approach, and then use just a small selection of the modes to essentially recreate a lot of simulations where we vary a parameter like the elasticity, and recreate all those simulations with, essentially in no time at all. So that's the proposed benefit. The computing those eigenmodes itself is of similar expense to doing the simulations, but you only have to do it once. So if you're doing some kind of parameter sweep, then it can be pretty useful. And that's why we think it would also be useful for tying in with inverse models, where we have to run lots and lots of iterations of the same model with slightly different parameters. We hope we can use this kind of method, maybe a slightly more improved version of this method in combination with some of the stuff I talked about earlier in the talk, to produce even better inverse models. So there's some possible other applications, other diffusion networks where Laplacian is the key operator. For example, the very small airways of the lung, which here are just included in these elastic bags. Other general circuit networks, some vessel networks in animals and plants. For example, the project we're looking at this summer is going to be based largely in placental vessels, where actually Poisson flow is a much more reasonable approximation. Or indeed, similar approaches could be adapted to mechanical networks instead. So effectively, we've seen that this dimensionality reduction we can get rid of about 99% of the number of equations we're solving, essentially, and still represent the system really well. But it is for a relatively simple system, so we're hoping to extend it to more complex systems in the future. And so this is what we plan to do next. And I think since we can actually read this, I think I mentioned all this already now, but since we can read it, I'll just leave that there, because that's the final slide, and open it out for questions.
Sure, Carl. Thank you very much. Very nice talk, very fascinating. I would, the chat box is open for people to ask questions, so please feel free to put in your questions or comments. And yep, there is Rhoda's question already. So I will, Rhoda, you are already a participant, so I would, you can ask the question.
Okay, thank you. So thank you, Carl. That was great. I was wondering, how realistic is your elastic bag assumption? You mentioned something about the elasticity not being homogeneous. But could you tell us a little bit more about how realistic it is to assume that your alveoli are basically elastic bags?
Yeah, so there's three ways it's unrealistic, I guess. There's the fact that there's actually some they're not perfectly elastic. There's a kind of surfactant layer in the lung, which means that expansion is actually kind of viscoelastic in some sense. There's the viscous layer lining the alveoli. So that's one thing. The second thing is that actually all these bags, not bags, all the elastic parts along are actually coupled together. So then they can't really be treated as independently inflating bags. They are, they are connected to one another, which is why really it'd be good to characterize this coupled motion as well. So if one part of the lung expands, it exerts some force onto the adjacent part of the lung. And there's a third one, which is that it's also, while you maybe think that elasticity is a reasonable assumption, there's also, it could be non-linearly elastic as well. And almost certainly, it definitely is non-linearly elastic if you stretch it far enough, but you can approximate it fairly well for, the kind of breathing that you would do in these sort of multiple breath washout type experiments where it's relatively shallow breathing, but deep breaths, certainly linear elasticity is not a good approximation.
Okay, thank you.
Carl, just to follow up on your eigenvalue and eigen analysis, is it possible to use these eigenvalues, for example, to characterize? So you can definitely characterize the function. Could it be used for as a biomarker for disease or its progression?
Well, that's hopefully one of the ideas. Yeah. So if you had a good image of all the airways down to relatively small scale, which you still struggle to get from CT, perhaps you get to sort of intermediate scale, but you would definitely get from micro CT, although that usually requires excised lungs, in which case it's too late to do much about it. But you can set the idea is you can characterize, I guess, the sort of resistance network that comes out of that. So you could either run a simulation and look at where the gas through this spectral and take the look at the large number, the region to be very under, tell you the regions of interest, I guess, in your tree and where the in that sense. So yeah, that is it's not entirely clear how that might relate. So to clinical practice, but it's definitely a potential, I think. I noticed a question from Neil in the chat as well.
Cool. Yes, Neil, I have.
Do you want to read that, or shall I just answer?
I think Neil, are you able to are you able to use your mic? Yep, there you go.
Oh yeah. I mean, it's just a couple of hopefully simple questions. It's really nice work. Cheers, Carl. It's good to see. Yeah. I mean, as a practical question, I was just thinking about the time taken for the simulations, and then computational power. I think for the first part, you were sort of saying it was quite a simple model. I was just wondering if you could kind of do it at the
so at the exactly. So the individual model takes no time really to run at all. The Bayesian process is relatively intensive, so you have to usually run tens of thousands of mod iterations, but that's still pretty quick. So at the fitting a single data set, it takes about a minute or so. I think at the moment I have that split over several cores, but I don't think that should make too much difference. You definitely can run it on a laptop, and because it's all kind of, it'll be slower on certain laptops than others and might take a bit longer, but it's very, very slow and it's not intensive to run at all. And the second part, the dimensionality reduction, in fact, the Yeah, the heterogeneity is an interesting one. So what how many eigenvalue you need, essentially, or how many eigenmodes you need to recreate your is sort of how deep into the tree your heterogeneity is. So when we had models, I showed it very briefly, but when we had, I don't know if I can go back quickly enough, but when we put, no, there we go. So G here is the generation from of the tree, which I didn't explain very well. So the blue is when we applied constrictions deep in the tree, you need more modes to recreate your system than you do when you have you essentially have constrictions higher up the tree. And that's essentially because if they're higher up the tree, then you essentially have a few contiguous regions that are different to one another, and you can capture. Turns out because of this kind of tree structure that's built into the operator, you can capture those with a relatively small number of. So yeah, it's not just the heterogeneity. Well, yeah, it's kind of how granular that ventilation heterogeneity is as well that seems to determine how many modes you need.
Thanks a lot.
Thank you, Neil. Thank you, Rhoda, for the questions.
Thanks,
I don't think there are any further questions at this point. So, Carl, thank you very much for agreeing to give this nice talk. This is fascinating, and for talking about not only just the clinical bit, but also explaining to us this new fascinating mathematical method. It seems like it could be used for many different applications. You already pointed some of them. Maybe one last question from my side would be, how does it change the application of this method if your trees branch out differently in different regions? I mean, somewhere they're dyadic, somewhere else where they're not.
Yeah, so as long as it's, then the method is pretty robust, I think. I mentioned before, so assuming that you can treat things as linear and things like that, then it's quite general. The problem is when you try and generalize to a system that's not a tree, this is not very useful because the operator and the tree you can't inverse calculation, which is would take a very long time. So the point we're trying to do now, a bit more general, is what operators becoming. The Laplacian, it turns out, which showed in this paper, which I haven't talked about here, is less useful when you get to these complex trees, as you mentioned, with with heterogeneity and lots and lots of branching. The Laplacian, the potential for dimensionality reduction is really poor. Sorry, it's telling me my internet connection has gone bad as well now. So I'll stop sharing.
Great. Thank you very much once again, Carl. I hope everybody enjoyed as much as I did. And have a nice weekend. And thank you. And maybe we'll have you here physically at some time. Bye.
Yeah.